Hi all, and welcome back to day 3 on distance protection. I'm Brandon Davies from TRC, and we'll be continuing on today to a little bit more of a deeper dive into distance protection schemes. So our agenda for today is do a quick recap of some of the key concepts we covered in day 1 and day 2. And we'll be taking a closer look at distance protection and some of the factors that impact reliability of those elements. Past just the basic settings that we discussed on the previous class, we have a lot of other external factors that can influence the decision-making process and selecting settings and in the end impact the reliability and operation of the elements themselves. So we'll be covering several of those and also taking a look at some other considerations that we as protection engineers might think about when we're applying a transmission line protection scheme. And then finally, we'll wrap up with a step distance setting example that will give you an idea of the types of calculations and analysis that we would do as protection engineers setting a step distance scheme. So I've provided this slide on the last couple classes as well, but I think it's important to relate back to these key system objectives of reliability and the balance between security and dependability, the importance of selectivity in making sure your protection is operating for the faults you want it to, and not for faults outside of its zone, so you can maintain as much of the power system as possible after a problem. Speed, looking at how fast we can operate for a given fault, and then simplicity and economics is some other factors we'll look at. So we'll certainly continue to try to frame a lot of the concepts we'll be talking about today within these terms. So I just wanted to go over this once again as a important factor to consider as we're talking about these schemes. So a quick recap of some of the concepts we covered in the previous class. So we took a look at distance protection in general, how the elements operate, what we do for setting those elements, and how those elements respond and what they see for operate quantities and different electrical measurements during both normal operating modes and fault operating modes. And then took a look at how we can use those differences in applying a reliable protection scheme that will provide coverage for the entire length of the line, as well as potentially backup protection for other parts of the system. So what I've got shown on here today is one of the examples we went through of a couple ways to represent a step distance scheme. We've applied 3 separate protection zones, zone 1 being an underreaching forward-looking zone that is set to ensure it does not overreach the end of the line, so it's only going to cover a portion of the line, but it's going to be able to operate instantaneously, so we're not going to have any additional delays added to the operate speed of that element. Because that doesn't reach all the way to the end of the line, we have our zone 2 protection, and zone 2 is set to look past the end of the line and ensure that it provides 100% coverage for the protected line plus some margin. And in this case, we've shown it as a 20% margin. Because that does overreach the remote bus and other protection systems, the zone 2 is going to have to be delayed so that we can coordinate with time coordination rather than sensitivity coordination for faults on the bus or adjacent lines. We'll allow those to operate their breakers and clear the fault on those parts of the system before we trip off this line that otherwise doesn't have a fault on it. So we want to minimize that system impact and maintain that selectivity of the system. And then finally, we provided a zone 3 remote backup protection scheme. So this is a very sensitive, very far-looking protection element that's set to look all the way past the remote bus and onto the longest line past that bus to ensure that it's going to be able to see faults on not just the protected line, but any other part of the system past that. And this is really provided in cases where you don't have breaker failure protection, you might not have redundancy in your protection schemes. There may be other considerations that would drive the need for that zone 3, but it's because it's so sensitive and sees so far into the system, it has to be delayed considerably to ensure that it's coordinated, time coordinated with other protections. So that would often have a delay of a second or more to provide that coordination if it is applied. So we're going to take a look at some of the other considerations that go into our transmission line protection. I want to talk first about loadability considerations. And loadability is really just, that, we want our protection to be able to operate for all fault cases. But ideally, if we're in a scenario where we're in a heavily loaded part of the system and there's a reason why the system operators are having to push the limits based on other outages or other considerations. The last thing we want is our protection operating to trip when it's just load current or load through the line rather than a fault current going through the line. So when we look at loadability, we really are mostly concerned with our phase distance elements within our step distance scheme. And that's because the ground elements are not going to be responsive to load. They respond to zero sequence quantities, which are really only present when there's a significant unbalance. And generally, loading on the transmission system is going to be fairly balanced. So you're not going to have that zero sequence component that you would need to operate the ground ground distance elements. So really, when we talk about loadability, we're really coming back to the core concept of reliability, dependability, and security. Um, and really, if we look at it from a security perspective, we're saying that we don't want the relay to operate for a condition that's not a fault. So when we talk about loadability, we're really talking about the security against loading conditions. Off to the right here, I've got that same Mo characteristic for the step distance scheme with the 3 zones, and then I've got a region that's shaded off to the right, which would be our load region. And as we discussed on the last class, your load is typically going to fall somewhere in the plus or minus zero point 0.9 power factor range. So it's going to be mostly a resistive load region where we expect the load to be able to fall. When we have faults, it's going to swing much more, reactive, and it's going to be closer to 70 to 80, 85 degrees. It's going to move over towards that line characteristic that we have shown in the plot. So when we're looking at loadability, we need to understand the limits of the angles that we expect the load to operate under, and either plus or minus 30 or plus or minus 35 are pretty typical ranges that we'll use and expect the relay to be secure for those areas. And then we're going to have a MVA rating of the line or the equipment that will be the basis for how much load we should be able to push through that line. And as protection engineers, we want to make sure that the protection that we set is not being the limiting factor there. Transmission lines are extremely expensive to build, so system operators and utilities want to be able to fully use the capabilities of those lines and not have the relays trip the lines out for load conditions. So looking at the figure over here, you can see that one of the corners of that load region is going inside the zone 3. So that means if the load is operating near that limit and at a angle near the upper angular limit of the load region, the relay is going to see that, and the impedance the relay measure is going to be inside of the Mo characteristic. And if it stays there for longer than the zone 3 timer, which would typically be about a second, the relay is going to trip off for that load condition. So we need to take a look at that and maybe consider ways we can adjust our settings and modify our scheme to prevent that from happening. And past just the desire to not trip off under load, there's actually some compliance requirements from NERC and a NERC standard PRC23 that applies to the bulk electric system, which is 100 kV and above. So pretty much all or most of the transmission lines we'd be using the scheme for. That says you have to maintain a certain amount of loadability, and your relays can't operate for the expected loads that the transmission line should be able to carry. Failure to comply with this requirement can result in large fines for non-compliance, and you'll have to go and fix the problem if it's identified. So the NERC PRC 23-4 requirement for distance elements is to set the transmission line relays so they do not operate at or below 150% of the highest seasonal facility rating for a circuit for the available defined loading duration nearest 4 hours. So typically when you're looking at transmission lines and their loadability characteristics, you're looking at seasonal ratings, so you're able to push more power through the power system and through the transmission lines in the winter because of the cooling effects of the colder temperatures. And there's different ratings for how long system operators can operate their transmission lines within those ratings. So typically you may have a 4-hour long-term emergency rating and a 15-minute short-term emergency rating, and maybe even a couple other ratings past that are based on thermal modeling of the transmission lines and the expected seasonal ambient temperatures and things like that. So the other criteria is very similar to the first one, except because you're using a higher rating. The 15-minute rating would be a higher MVA or current rating than the 4-hour rating. The criteria is a little looser, that you have to be make sure your relay does not operate below 115% of the 15-minute facility rating. And in either of these cases, we're evaluating relay loadability at a reduced voltage, which will increase the current, and a specific power factor of 30 degrees. So that's where, when you're plotting out your load region and looking at your loadability compliance, that's where that 30 degrees comes from, that we've got plotted in the load region shown on that figure. So I've got another diagram here that gives some math behind how you go about calculating the loadability limit based on a Mo characteristic at a given max torque angle, and the loadability requirements that are outlined in NERC PRC 23. So the parameters that we have on the figure there, ZR is your relay's phase distant element reach, and this would typically be your longest reaching tripping element. So if you've got an element that's going to operate to trip your line, you'll look at whatever the largest reach is, because that's going to generate the biggest circle and have the most likelihood that it would come into that load region. ZL is your loadability limit. So this would be the point where at the given angle, that's how much load you would be able to put as an impedance. We've got the maximum torque angle as well as the load angle. So the load angle is that would be the 30 degrees criteria, or potentially you may try to set it slightly above that at 35 degrees or something like that to make sure that you're um, considering something outside the NERC criteria. But generally, we'll use 30 degrees for that, and then the max torque angle is generally set to the transmission line impedance angle. So the equations that I have shown here for the loadability calculations will, you can use them to calculate the loadability limit at that given angle for an element. And then from there, you can use that to calculate a maximum power transfer at that angle based on other conditions like the voltage magnitude you're considering and things like that. So these can be used to calculate that loadability of an element based on that given consideration. So we can take the equations from the previous page and the way we went about finding that loadability limit of that element, and we can expand on that to apply that to the NERC PRC23 requirements. So as I mentioned, the NERC load limit must be checked against 150% of the highest facility rating for the line using the 4-hour rating. And we get a look at that at 85% voltage and a 30-degree load angle. So ISO New England bases their facility ratings on a few different definitions. And this is all stuff that is done through thermal modeling analysis and evaluation of every individual line. It's something that's looked at for every piece of equipment throughout the power system. The normal rating is a continuous 24-hour rating. So at your normal rating, you're able to operate forever, and you won't have any thermal damage to your conductors or any loss of lifespan of that equipment. The long-term emergency rating is a 12-hour summer or a 4-hour winter rating. And that's called the LTE, and generally it's the summer or winter LT is what you describe there. The short-term emergency rating is a 15-minute rating, and then they also define a drastic action limit, which again would have a summer or winter criteria. And this is a 5-minute rating. This is absolute worst case. You can operate the system like this for a very short time while you provision the system to hopefully offload some of the loading on the line that is at that limit. So if we take what we learned in the previous slide, we can use the loadability calculation that compares the line angle or the maximum torque angle minus the load angle, 30 degrees in this case because that's the NERC requirement, against the longest protection element, phase distance element. We can use that to calculate a primary impedance, basically between the origin and the upper corner of that NERC load region. And we'll compare that to the impedance that we would see for load operating at rated current, but also at 0.85 per unit voltage and 150% of that current rating to meet the loadability criteria. And if you do this calculation and the loadability reach of the relay is less than that calculated NERC limit, you're all good. You don't need to do anything to adjust your settings. Loadability is going to be maintained. If it doesn't, if your loadability of the relay is higher than the NERC limit, you're going to have to do something to adjust your settings to make sure you maintain compliance. And there's a few different methods we'll take a look at. We can accomplish that by using. So generally, the main approach that utilities use if you run into loadability requirement compliance issues is to apply a element called load encroachment within the relays. And what load encroachment does is basically it blocks a portion of your phase distance element response so that the relay will not operate for that measured condition. And when you do this, the load encroachment characteristics come in a few different varieties, but most come in a way that it's set basically to mimic the load criteria. You set them with a um, impedance reach that defines the kind of circular inner portion of the characteristic, and then an angular setting that'll define the angle in which you'll block. So what we've got shown here, we've got a load region shown in blue, and then the load encroachment region is set to have a slightly larger angle and a slightly lower impedance setting compared to the impedance that is calculated for your NERC loading criteria or other loading requirements. And what this does is it makes it so anywhere, if you have an impedance that falls within the pink shaded region or dashed region, uh, even if it falls within the zone 3 characteristic or any of the other distance element characteristics, it will be blocked from operating. The logic within the relay will prevent a trip from happening within those those areas. All right, so next we're going to take a look at a step distance scheme calculation example. And once we go through this fairly simple, straightforward uh, application, we'll talk a little bit more about some of the other kind of unique aspects that you might run into for some more complicated transmission protection applications. So we'll start out taking a look at our phase distance calculations. So as we talked about, you're going to operate and set your relay based on a few different criteria. One is the reach, an impedance reach of how far down the line the relay is going to look. You're going to need to know your maximum torque angle of the line, and that's generally set to mimic the transmission line impedance angle. And we're also going to need to know about loadability of the line because we're going to be stepping primary measurements of primary currents and voltages down to secondary quantities. We're going to need to know some information about our instrument transformers, so current transformer ratios, potential transformer ratios. And we'll use all that information to go through a series of calculations and determine the appropriate settings we'd load into the relay to have it operate for uh, the application in the way we want. So taking a closer look at some of the input data, we've got our line here, line 1, and a lot of the stuff we're going to be able to pull right out of Aspen one-liner. So if you go and look at the transmission line model within Aspen, you'll see that everything's set up in per unit. So here we've got positive sequence and zero sequence impedance parameters in a rectangular form, so R plus JX type form. And those are per unit on the system base. And by default, Aspen uses 100 MVA base. You can configure it for something else, but I've really never seen that done. Generally, that's what everybody is using for their system base. Within the model, you'll also be able to tell how long the transmission line is. In our example here, we've got a 14-mile transmission line, and the system is operating at 115,000 volts, 115 kV line to line. We would generally get a facilities rating sheet from the utility that we'd be working with, and that would provide the applicable ratings for summer and winter ratings, such as the short-term emergency and long-term emergency ratings. In this case, we've got a 300 MVA rating for the 115 kV transmission line. And then we dig into the drawings, the site drawings, to get some information about the current transformers and potential transformers that we're using for this relay. Generally, we'd be pulling those off of the relay one lines or three-line elementary diagrams to get some nameplate information and understand, not only what the ratings of the CTs and PTs are, but also how they're connected. Oftentimes they'll have multiple taps, so you can adjust the ratio by wiring to a different portion of the instrument transformer. So we're going to want to understand what the actual connected ratios are. And in this case, we're looking at 1200 to 5 or 240 turns for the CT ratio. And we're stepping down from, we're using a line to ground connected PT, and it's connected from 66.4 kV down to 66.4 volts. So we've got 1,000 to 1 turns ratio on our potential transformer. So the first thing we'll do is we'll need to define our per unit bases that we'll be using for our calculations. And the MVA base is already defined from Aspen. As I mentioned, it's typically set to 100 MVA. But we're also going to need to be able to convert voltages and impedances from per unit to secondary ohms. So we can define our voltage base at 115 kV line to line, and then our impedance base is going to be calculated using the voltage base and MVA base, and will be set to 132.25 ohms. And we can use that Z base to take the per unit impedance from Aspen and convert that into a value in ohms that we can use for our calculations, because the relays are typically going to be set based on secondary ohms. So we'll take the per unit, calculate it to turn it into primary ohms, and then we can use the CT and PT ratios to turn that into the secondary ohms that we'll be using to set our relay element. So I've shown that calculation here, basically taking that per unit quantity and using Z base to convert it into a impedance quantity in primary ohms. And then those values can be used using the CT ratio and PT ratio to calculate the secondary quantities. And generally, when we're looking at this, we really are more concerned with the impedance magnitudes and angles than we are the components of resistive and reactive components of those. So generally, we'll convert those into a polar form, like I've shown, where we've got 2.5 ohms secondary at an 80-degree angle for our positive sequence magnitude and angle. And then for our zero sequence impedance magnitude, we calculate that out to 8 ohms secondary and 70 degrees for the angle. And we'll use these as a basis and starting point for the rest of our settings calculations, because now we know how the relay views the impedance of the transmission line we're trying to protect, because we're going to be making all those measurements in secondary quantities. With the secondary line impedance calculated, we can now move on to calculating our phase reach settings. So the zone 1 is where we'll start, and as we discussed previously, that's typically set somewhere between 80 and 90% of the transmission line impedance. And that's to ensure that it's going to underreach and it's not going to trip for faults past the end of the line, and that margin is there to ensure that. So if we take 80% of our calculated zone 1, positive sequence line impedance magnitude of 2.5 ohms, we get a zone 1 setting of 2 ohms secondary. And then that's what we plug into the relay and configure in the relay settings to apply that zone 1 element. With most relays, you don't have to independently apply the torque angle. We know that the line angle, positive sequence line angle, was 80 degrees. But we also put that line impedance information into the relay. So the relay, many relays already know what that line angle is, and by default set the impedance characteristic to align with the line impedance angle. Anyway, there are some varieties out there that you would set that separately, which you certainly can do, but in many relays, it's done automatically. We can take a similar approach for the zone 2. So the philosophy we talked about was to set it with some margin to overreach the remote end of the line. And that's to ensure that we're providing coverage for that last 20% of the line that isn't protected by zone 1. And we want to make sure we've got enough margin so that we know that last portion of the line is going to be covered. So similarly to what we did for the zone 1, all we have to do is take that positive sequence impedance magnitude, the secondary quantity that we calculated, and multiply it by the margin we want to apply, so 120%. And then from that, we can get our step distance zone 2 set point of 3 ohms secondary. Now that we've set our uh, distance element reaches for our phase elements within our step distance scheme, we got to check a couple things to make sure that the relay is going to maintain reliability, both security and dependability, for all expected faults. So in particular, the zone 2 element we know is going to be reaching past the end of the line through the remote bus and into a portion of the next lines. So it's going to see a portion of the way onto line 2 and a portion of the way onto line 3. But we have no way of knowing without doing some analysis if that zone 2 element is going to be overreaching and overlapping with the zone 2 element on those adjacent lines, line 2 and line 3. So one of the checks we'll typically do as part of our settings evaluation is run faults on those lines and verify at the boundary of the remote zone 1 what impedance the relay we're setting will see and if it's going to trip for that or not. So the way we go about doing that is generally using Aspen. We're able to pretty accurately model the system and show relay responses. So we'd run faults throughout each of those remote lines and see the ending point where the line 2 zone 1 element stops operating. And at that point, we're operating on a time delay. And we'll verify that the line 1 relay is not operating for that condition. If it is, we might need to consider applying a longer time delay or reducing the reach or doing some other method of determining preventing the line 1 relay that we're trying to set from operating at the same time as the protection on line 2 or line 3. So the calculations I've got here is basically we're taking an apparent impedance. This is the relay seen by the line 1 relay we're setting for those worst case faults. And we get that in primary ohms and we convert it to secondary ohms. And we check to see if our zone 2 reach is higher than those values. If it is, then we might want to go in and make some adjustments to our settings, adjust the timing or adjust the reach, do something else to mitigate that problem. So in this case, the apparent impedance seen for those remote faults was 4 ohms and 6 ohms, which are well above our proposed setting of 3 ohms secondary. So our settings are adequate, and we can use a standard 18 to 20 cycle timer for that zone 2, and we don't have to worry about that coordinating with the remote zone 2 elements on those other lines. All right, so next we will take a look at our NERC loadability. So this will be checking that NERC PRC23 loadability requirement. In this case, we're looking at criteria 1, which is uses the 4-hour rating, winter rating in this case for our worst case rating. And we need to make sure that our relays is not going to operate for the currents below 150% of that rating at 0.85 per unit voltage magnitude. So the first step is to calculate the current rating itself. So we'll take the winter LTE rating, which is 300 MVA, and we'll use that to calculate what the current magnitude would be for that loading condition. In this case, it's 1,506 amps primary. We'll then use that to calculate what the maximum allowable relay reach is based on the other criteria, the 0.85 per unit voltage and 1.5 or 150% of that current rating. So the second equation here does that calculation, and you can see that the loadability point is going to be 24.98 ohms primary, and that's how far the load region would show up on the RX diagram. That's the upper corner of that load region that kind of defines the circular portion of that. And then lastly, we need to compare that value, the maximum allowable relay reach, to what a relay is actually reaching at the 30-degree loadability criteria. So we'll use that relay loadability or element loadability calculation where we use the line angle or the max torque angle and then the angle of interest, in this case 30 degrees, to calculate the relay's reach at 30 degrees based on its worst case or largest protection element, tripping element. So in this case, our relay at 30 degrees is going to reach just about 8 ohms primary because that is less than the maximum reach allowed before you have a loadability issue. Your NERC loadability is met with these settings. You don't have to apply load encroachment. You don't have to adjust your reaches. You don't have to do anything like that to meet this compliance requirement, and the system operators will be able to operate within the constraints of those line ratings. So that wraps up the phase protection. What about ground distance settings? So ground step distance elements operate on zero sequence impedance quantities that are calculated based on zero sequence currents and zero sequence voltages, and are set in a very similar way to the phase distance elements. So similar to the phase distance example we just set, we would have a zone 1 element set to underreach the remote bus, and we'd have a zone 2 element that would overreach the remote bus, and between those two they provide full coverage for the line, with the zone 2 providing a time delayed element. So in most relays, the settings for ground distance elements are configured using the same positive sequence impedance settings as we calculated for phase distance elements. And this is done mostly for simplicity. It allows you to see the equivalent reach of your phase element versus your ground element. You're going to be basically seeing the exact same settings of 2 ohms and 3 ohms for zone 1 and zone 2 that we calculated. And then the relay uses a compensation factor to internally take those positive sequence settings and turn them into what the relay is actually using to evaluate the zero sequence quantities. So generally there'll be some kind of a compensation factor or setting adjustment that you provide within the relays that makes that adjustment for you. And for Schweitzer relays, it's this K01 factor that I've got shown down here. That basically we're taking the zero sequence impedance, subtracting the positive sequence impedance, and dividing it by 3 times the positive sequence impedance. And that setting, both the magnitude and angle, tells the relay how to take that positive sequence setting and convert it into the equivalent zero sequence setting without you actually having to go do the zero sequence calculation separate from the phase calculation. So the reaches themselves are pretty straightforward. We're just going to take the zone 1 ground reach and set it equal to the zone 1 phase reach. They're both set to 2 ohms secondary. And we'll do the same with zone 2. Set the ground equal to the phase, and that will be equal to 3 ohms secondary. Then we can take our positive sequence and zero sequence impedance values, and this will work either with primary or secondary quantities where it's a unitless quantity we're calculating here. And we'll use the K01 equation here to calculate a K01 magnitude and a K01 angle. And this represents the magnitude shift and the angular shift that we'd expect moving from a positive sequence impedance calculation to a zero sequence impedance calculation within the relay. So that wraps up the calculation example. In general, that was a fairly simplified protection application. Generally when you're actually setting a transmission line relay, you'd be applying several other schemes in parallel with that. You might be providing a directional ground overcurrent scheme, a switch on default scheme. You may be pairing that up with a pilot scheme or a communication assisted line protection scheme. But in general, when you break down the approach to any of those, they're all fairly simple schemes. You just really need to understand the reasoning behind why you're setting them that way, so that you can make sure that between all of those schemes, you're covering all of the expected fault scenarios that you'll need to operate for. So that was a fairly simple application. What other things are out there that you might run into when you're setting transmission line protection relays? So I've got a number of things listed here, and we'll be covering these at a very high level for the remainder of the topic today. These are all considerations that you may want to look into if you're looking at a more complex transmission application. So the first one's line length and source strength. So we do a calculation called source impedance ratio that tells how strong the system is behind the line, which can have an impact on on how well your protection is going to operate. You may need to adjust some of those typical set points and philosophies for how you're applying your margins to those lines if you've got a source strength issue behind you. There's also zero sequence mutual coupling, and we talked about this a little bit in day one, that if you have multiple transmission lines running down the same corridor, you can have a coupling effect of fault currents from one transmission line coupling over to the other transmission line, which can impact the measurement quantities your relays are seeing and thereby impact the reliability of those elements. So it's something that needs to be understood, it needs to be modeled, and it needs to be addressed in your settings. There's also in-feed effects. If you have tapped loads, or you've got a multi-terminal line, if you've got some other source that is coming into your transmission line, it can impact the measured apparent impedance that you will see at each terminal for different faults, because you've now not got just the same fault current and voltage drop across the line, where you have that additional current source coming in. You're going to have differences in what each portion of the line is, which can impact your protection evaluation. There's also power swings. So, the power system is a very, very dynamic um, system. It's not as simple as what we model in a time domain steady state type of modeling software like Aspen. So there's a lot of things that can go on with control interactions and things like that on the power system that can cause strange measurements and unexpected measurements within the protective relays. Um, so we need to take a look at that to make sure that we're setting our relays in a way that they're going to maintain reliability for those scenarios. And there's another one of the NERC PRC standards that provides some guidance on how to set your relays in a way that you know, they will be secure during stable power swings. There's also loss of potential. What is going to happen to your protection scheme if you blow a fuse on one of your line VTs? How is it going to operate when you lose one of your sensing um, methods, which is your voltage connection? Really need to understand how it responds to resistive faults. So especially for single line to ground faults, there's a high likelihood that you're going to have some fault resistance associated with the fault. It's not just going to be a nice straight direct connection between the phase and ground when that fault happens. So how does that impact your protection sensitivity and the evaluation that you put into that? And then we've got some other things we can look at. I mentioned early in the day one that there's also some other types of impedance characteristics past just the Mo characteristic, the circular characteristic. So there might be cases where you want to apply some of those other characteristics to deal with some of these other considerations. We also have some other considerations for coordinating with other types of equipment. So if you've got a transformer for a distribution substation that's tapped off our line, we're going to need to coordinate with that and make sure that our protection is set up in a way that it's going to maintain a connection for that tapped load. And then lastly, not all transmission lines are nice, straightforward two-terminal lines from one station to another. There's many applications out there that have multi-terminal lines that really add a lot of complexity to the protection um, system and meeting the protection objectives that we've discussed. So the first one of these considerations we'll take a closer look at is source impedance ratio, or SIR. And SIR is basically looking at the Thevenin equivalent source impedance behind the relay compared to the impedance of the line. And that would be evaluated both with all lines in and certain outage considerations. What that gives us is a quantity that we can use to understand um, electrically the length of a line, if it's electrically a long line versus a short line, and that'll impact how we look at the measurement quantities we're using to do our distance element calculation. And the line length isn't quite as straightforward as the physical line length. You could look at it and say, okay, this is a 50-mile long line. It's physically very long. This is really looking at the electrical characteristics of it. You could have a very short, physically short line, or a moderately short line with a very strong source behind it that would still look like a long line electrically. Similarly, you could have a fairly long line with a very weak source behind it, and it would look like a short line. And that's really a way for us to understand electrically what's going to happen, specifically with the voltage that the relay is seeing for various fault cases, and how that voltage divides between the source impedance, the Thevenin equivalent impedance behind the relay, and faults on the line. And that'll impact our are relay measurement errors, because if we have a very low voltage for faults we need to operate on, we're going to have a higher amount of error, which is going to make it more challenging for the relay to determine uh, a accurate measurement for the impedance at that location because of the extra errors. So basically, what that does is it if we've got a very high SIR on our transmission line, we are going to probably consider reducing our zone one reach, because for a fault on the line, if we have a high amount of error, that 20% margin by setting it at 80% may no longer be adequate to ensure that the relay isn't going to overreach the remote end. So I've got a table here. It's from a Schweitzer technical paper that's a great reference, but it gives a graph here of kind of an idea of where you may want to consider setting your zone one margin based on different calculated source impedance ratios. So this is one of the things we definitely want to look at when we're doing transmission line applications, so that we understand the system a little bit more and can get in front of some of these challenges with high source impedance ratio applications. So the next thing we'll take a look at is mutual coupling. So as I mentioned a couple slides ago, you know, mutual coupling happens when you've got transmission or subtransmission lines running in the same right of way or sharing the same tower, and that they're close enough for the zero sequence current on one line to induce a zero sequence current voltage on the other line. And this can occur with lines on the same or different voltage magnitudes. And in general, positive sequence and negative sequence mutual coupling can be neglected. Zero sequence mutual coupling affects ground distance elements and ground overcurrent relays, and is a much bigger concern than the positive and negative sequence, where those are balanced phasors. They kind of cancel the effects out between the phases. The worst case minimum and maximum apparent impedances for the relay need to be looked at, so we can understand if we've got an issue where the zone 1 relay may be overreaching in certain cases. We also can have cases where the zone 2 relay may be underreaching in certain cases. So we really need to look at how the relay responds to all of these conditions during system normal operation, so all lines in, with the mutual coupled lines taken out of service, and then finally with the mutual coupled lines taken out of service and grounded, so we can see how the system's going to respond. Generally, this type of analysis we're going to do directly in Aspen. We're able to model the mutual coupling impacts within the transmission line models. So Aspen can do a good job of evaluating and showing us how those relays would respond, and we would simulate dozens or even hundreds of faults within the surrounding transmission system to make sure that for all cases that we had a in-section fault, the relay is operating the way we expected it to, and for any of those faults, outside of the line, that we're not tripping instantaneously on that zone 1 element. So the next thing we'll talk about is infeed. Infeed occurs when you have a tap or a generation station or some other source that's connected midway through the protected transmission line. And what that's going to do is it's going to make it so that the different portions before and after the tap are going to see different fault currents, and they're going to have different voltage drops and different impedance measurements over those portions of the line. So it's basically your current through one terminal is not going to be the same as the current through the other terminals. which is going to impact what the relay sees for apparent impedance measurements during that fault. So in general, your relay is going to end up measuring higher impedance and cause the relay to underreach the desired location when the infeed is present. So you really got to look at it from a perspective of both with the infeed being present and also with an outage on that. So if it was a generator, you may want to look at that, and you want to make sure that the relay is going to respond appropriately and for both of those conditions. So really, we're again looking at the same stuff. We want to make sure for all expected operating modes, our zone 1 element is underreaching the remote bus, and for all expected operating modes, the zone 2 element is overreaching the remote bus. And that ensures that the whole line is protected for either of those conditions. Your zone 3 calculations may not be as impacted by this because, again, you're already looking at worst case infeed when you're calculating that, and they're looking so far into the system that the impacts of the infeed are going to be less than some of these these other zones that are much less sensitive. So the calculation shown below the figure here, so the figure, we've got terminal S, T, and R, so sending, the tap, and then receiving stations. And you can see we've got infeed coming from a generator, from some other source connected to the tap. So the current between terminal S and the tap for that fault at bus R is going to be different than the current between the tap and bus R because we have to add in the additional current from the infeed. And IR is going to be the sum of IS plus the infeed. So rather than the relay directly just measuring the full impedance from S to R as it would if there's no infeed present, you're actually going to need to calculate and scale that up based on the ratio of the IR and IS to calculate what the actual apparent impedance the relay would see is. And you can see from this that because IR is IS plus the infeed, that ratio is always going to increase the apparent impedance seen by the relay. So in general, when infeed is present, your apparent impedance for a fault is going to be higher than it was before. So again, we can do some analysis in Aspen to see this impact. And it makes our calculations a little less straightforward than if we were just taking the transmission line impedance and adding our margin to it to set the zone 1 and zone 2. So when you've got this type of case, you really got to take a very close look at the protection, how the system responds, and again, look at both cases where the generation or whatever's causing that infeed is in service, and also when it's out of service, because we're going to have to cover both of those operating modes. So the next thing we're going to take a look at is the relay's response to stable power swings. And this is NERC PRC26, another one of the compliance requirements utilities and transmission owners are required to document and comply with. So what PRC26 says and what it requires is that you set your relays in a way that your instantaneous tripping or anything that operates faster than 15 cycles need to be secure for stable power swing conditions. And they provide some guidance on what those conditions should look like, what the region should look like. Very similar to what they did for loadability requirements. They're giving criteria of how they expect your relays to respond for certain conditions. And what NERC has provided for criteria is based on a system separation angle, which is the criteria they're using to decide between what is considered a stable power swing and an unstable power swing. For unstable power swings, there may be some other schemes you want to apply to separate your system and prevent larger system issues that can come from an unstable swing. But in general, what they're trying to accomplish with this is preventing us from being able to trip the relays for a stable condition. So there's a whole lot of math and a whole lot of stuff that goes into determining what that stable swing region looks like, but we're able to plot it and show it on our X diagram along with our distance elements. And it's this dashed line in red that kind of sweeps in and then cuts off in the middle and then has another characteristic on the bottom. And this dumbbell-shaped characteristic represents the area where a swing is expected to be stable, and therefore you should not be tripping your relays. These swings don't operate as fast as faults, but the criteria NERC provides gives you 15 cycles. So if for example, if your zone 2 timer is set higher than 15 cycles, you don't have to be concerned if the swing region comes into that zone 2 element. Similar to the load encroachment, if that region, the stable swing region, does enter one of the protective elements that will operate faster than the 15 cycle limit, you need to do something to block that operation. So what we've got shown here is solving that by applying a load encroachment blinder with a higher angle and a different reach than we would have for otherwise provided for PRC23 compliance. But basically it has a similar function where it's attempting to block out any areas of non-compliance to prevent the phase distance element from operating. A lot of this analysis and these types of checks they're all built into Aspen, so they can be kind of cumbersome to do by hand, but luckily we got some really great tools to help us understand how our protection is going to respond to help with that. So the next thing we'll take a look at is what happens if the fault has some resistance. So in general, we've been talking about this RX diagram and what happens to the measured impedance and the apparent impedance seen by the relay between load and fault currents. And in general, we've been talking about when you hit the fault, the impedance measured by the relay is going to be somewhere fairly close to the line impedance angle. Well, if you start adding resistance to your fault, and that could be the resistance of the ground itself, it could be the resistance of whatever made contact with the line. But if you add some fault resistance to it, that may no longer be the case. So basically, as you're adding resistance to your fault, you're going to be moving off to the right into that resistive, towards the resistive axis of the plot. And as that pulls, the increasing resistance pulls the measured impedance further and further away off to the right, it's gonna stop residing eventually in your distance relays. So, if you're in an area that you expect to have, resistive faults, that type of fault would be something that the utilities have seen before and want to plan for in their settings. They may look to see if you can model and set your protection to ensure it provides a certain amount of resistive coverage. And in Aspen, you can, while you're simulating faults, you can add a fault impedance resistance to that, and that's the way we usually go about evaluating that. The plot I've got off to the right here is probably a fairly extreme example. You can see the fault, impedance is well outside of those Mo characteristics. So if that's a fault that we want, an intersection fault that we want these relays to operate for, in this case, with the amount of fault resistance that this was simulated with, the relays aren't going to operate. So we'd need to take a look at other options of how we could provide dependability within those elements. So, the main type of fault we're concerned with fault impedance is ground faults, single line to ground faults. Because for a three-phased fault, it's unlikely you're going to have a highly resistive three-phase fault. Should be driving some unbalance there that you'd be able to detect with your zero sequence protection. So if we do have a case where we want to provide more resistive coverage, we've got a couple options. Probably the most common one is to provide a quadrilateral distance characteristic. And this you can kind of shape the element a little bit more. This is that rectangular characteristic to increase that resistive coverage to a value to cover the types of faults resistive faults you're trying to detect. You can also provide some other types of protection that may have increased sensitivity. So you may consider applying ground overcurrent protection either in a pilot scheme or as part of a standalone directional ground overcurrent, time overcurrent relay. And those can be set fairly sensitive and may do a better job than your distance characteristics in detecting resistive ground faults. So this example here is just really showing a couple of the other impedance characteristics. They might see the one on the left here shows a quad characteristic. You're able to not only set the reach of the element in respect to the transmission line. So this is shown somewhere around that 80% coverage of the transmission line. But you're also able to set how far into the resistive axis the element's going to see, and that allows you to provide a much more a much wider characteristic for resistive fault coverage that you otherwise might not be able to have with a traditional Mo characteristic. This is something that's generally only used for ground distance elements. Again, as you're pushing into that resistive axis, if you did this for a phase element, you would potentially start pushing into your loadability region. So generally, we're only going to see this on ground distance protection. The other type of impedance characteristic I've shown off to the right here is a lens characteristic. So this is something that really the only time I've ever applied it was when we had a PRC26 compliance issue, and we weren't able to mitigate it with load encroachment blinders. So you're able to set this element, you're able to set it with a longer, with the same desired reach compared to the line impedance, but basically allows you to kind of squish in the size of that circular characteristic into this kind of lens or football shape, so that you can choose how far into that resistive axis you go. And in this case, it was to move the operate characteristic, so it isn't encroaching into that stable swing region. So again, you get a couple different options on what you can do with different impedance characteristics that really are there for very specific reasons and unique applications. So to wrap up, we went over a fairly straightforward transmission line settings calculation example. We took a look at that, but then kind of went over some other more unique considerations that there may be for some more complex situations. And really, there's several factors that you must consider in distance protection. They're not all as simple and straightforward as the easy example that I gave in the class today. And model relays provide you a lot of flexibility, a lot of different schemes, a lot of different ways you can do that. And also the simulation software we have gives us a lot of knowledge pretty easily to be able to validate that the settings we've chosen meet these requirements. And lastly, really the typical settings practices are going to cover you for most cases, but it's important to understand some of these unique factors. And accurately model the power system so that you can evaluate if those typical settings, philosophies, and practices are going to be adequate for any application, even if it seems very straightforward. So I also provide some additional references and reading here. If you're interested in taking a look at some other references on transmission line protection, these are all really great papers and books and IEEE standards that you can look at. Particularly the second one, the transmission line settings calculations beyond the cookbook. It's a paper Schweitzer engineers put out about a decade ago. That is a really great primer on some of the considerations for transmission line settings, and it's a reference I always recommend our new engineers go through as they're taking on their first transmission line setting example. All right, well, we will end there for today. Thanks everybody for listening in. Next time we will be taking what we learned on the last few classes, and we will be taking a closer look at transmission line pilot protection, which is a way we can provide faster and more reliable protection for a transmission line by using a communication channel between the two relays on either end of the line, sharing a small amount of information to make a more informed decision about a trip decision. So we'll talk about more about that next time. Thanks again.